Okay, so this is going to be a fairly quick little video that starts us on the road to balancing redox equations, redox reactions. And so we're going to look at half reactions, which you already have seen very briefly in the previous video. So why don't we get started? Here is a simple reaction. Synthesis reaction for the formation of KCl. So we can write an equation for that. Potassium plus chlorine yields KCl. Now, we can balance that equation pretty easily, but I'm actually going to balance it using half reaction. I'm going to balance the half reactions. So there are two half reactions present there. There's a half reaction that involves potassium, and there's a half reaction that involves chlorine. So why don't we get those down? These half reactions have to reflect the changes in oxidation state of the constituent atoms, so that's potassium and chlorine. And from those changes in oxidation state, we can balance electronically. So that's really the idea behind half reactions. You're going to balance the electrochemical component of it, and that is basically charge. So let's get our two half reactions first of all. So here's potassium. So potassium yields the potassium ion, K+. And chlorine gas, chlorine, yields the chloride ion, Cl-. So those are the two half reactions. But as I said, they're not balanced. They're definitely balanced by mass. One potassium has the same mass as a potassium ion, K+. An electron does not weigh very much, so losing one isn't a big deal. But here, Cl2 is not balanced with Cl-. There's two chlorines to one chlorine. Again, electronically, we don't worry about the mass of electrons. But the other thing is the charges aren't balanced. K with a neutral, in a neutral state, 0, charge of 0 versus K+. 0 does not equal 1+, so they're not balanced electronically. So that's what we're going to do, balance electronically. So how do we go about doing that? We add electrons. So in the process of adding electrons, we can balance. So 0 and plus 1. We have to make those two charges equal by adding an electron, which is a negative charge. If we added a negative charge here, 1 minus does not equal 1 plus. 1 minus and 1 plus are not the same charge, so we're going to get rid of that, and we're going to go to the other side. So if I add an electron here, I now have 0 on the left-hand side, and I have plus 1, minus 1, I have 0 on the right-hand side. So that's balanced. And so if you look at what's happened here, potassium has yielded a potassium ion and an electron. That's a loss of electrons. There's an electron over here that this potassium element lost. So this we can identify as an oxidation. So for oxidation half reactions, we always add electrons to the product side. An electron is a product of an oxidation. Let's look at our other half reaction. And so this is going to be a reduction. In terms of balancing, we balance by mass first. So we're going to balance the chlorine. So there's 2 Cl. So now it's balanced by mass. But again, it's not balanced by charge. 0 on the left for the elemental chlorine. 2 times 1 minus on the right for the chloride ion. So 0 and 2 minus are not the same. So we're going to add electrons. We add them on this side. When we add 2 electrons here, we have 2 minus on the left. We have 2 minus on the right. That's now balanced by charge. So balanced by mass, balanced by charge. And again, we've added electrons on the reactant side. And that's the definition of a reduction, right? A reduction is a gain of electrons. So they have to be present to be gained. So chlorine is going to gain electrons. They're the 2 electrons it's going to gain. And so that's the simple process of balancing half reactions. So Fe to Fe3+, we're going to balance this half reaction identified as an oxidation or reduction. So it's balanced by mass, definitely 1 Fe, but it's not balanced by charge. 3 plus here, 0 here. So to balance that by charge, we're going to add 3 electrons on this side. So 3 minus, 3 plus, 0, 0, and so because we added them to the product side, that is an oxidation. The iron species has lost 3 electrons. They're the 3 electrons it lost. O2, O2 minus. So oxygen to oxide. Not balanced by mass or charge. So to balance by mass, put a 2 there. Now it's not balanced by charge equal. or also, so we have 2 times 2 minus, that's 4 minus. So we're going to add 4 electrons over here. So they're the 4 electrons that the oxygen species are going to gain to make them the ion. And so that, again, is a reduction because we've added to we've put electrons on the reactant side. Electrons to be gained are reactants. Okay, so now here's another task you're going to be asked to do. Given a following reaction, identify the 2 half reactions and identify them as oxidation reduction. So again, this leads into balancing more complex reactions. So let's first of all split them into our 2 half reactions. That's pretty evident. Tin 2 plus yields tin 4 plus. So that's 1 half reaction. And the other half reaction is Fe3 plus to Fe2 plus. So there are 2 half reactions. So now they're not balanced. They're both balanced by mass again, but they're not balanced by charge. So to balance by charge, we're going to add electrons. So 2 plus and 4 plus. How do we make those 2 charges add up to the same number? By adding negative charge. Well, if we add 2 electrons here, 2 plus and 4 plus plus 2 minus. So that's 2 plus, that's 2 plus. So electrons as a product, that's an oxidation. Second one, Fe3 plus to Fe2 plus. So how do we make those charges the same? We're going to add an electron here. So E minus plus 3 plus is 2 plus overall, and we have 2 plus on this side, and so that is our reduction. And so that should again make sense to you. You have a balance. You have a redox reaction. You have to have an oxidation and you have to have a reduction within that redox reaction. Okay, so that's how you can simply split things into half reactions. We'll look at this in more detail later. Okay, finally, one last thing, balancing reactions in aqueous solutions. So this one it gets a little different. If we look at this half reaction, chromium 3 plus going to Cr2O7 2 minus. So this is a half reaction, but you'll notice we have these oxygens here. So we have oxygen now as part of a half reaction. So really this is about dealing with oxygen and hydrogen in the process of balancing a half reaction. If we were to try to identify this as an oxidation reduction, we can assign oxidation states +3 for the chromium 3 plus, and for the oxygen -2, and therefore that makes the chromium in dichromate on +6. So +3 to +6, that's an increase in oxidation state. That's an oxidation. So balancing it, well, we balance by mass first what's been oxidized. And so in this case it's chromium. Cr3 plus is oxidized. We're going to balance that species. So I just put a 2 there. Now I have 2 chromiums. And I have 2 chromiums. So that's balanced by mass. Next, we're going to balance the oxygen. And how are we going to do that? Well, it's pretty easy because these are aqueous solutions. When they're aqueous, what's happening? Or where's this reaction happening? It's happening in water. So we're just going to add water. So how do we add sufficient water to balance the oxygen? Well, it's easy. Over here, we add 7 H2Os. So 7 times oxygen, 7 times oxygen. Now the oxygen is balanced. But here's something. Now we've introduced this hydrogen in the water. So how are we going to deal with that? Well, again, a lot of these half reactions take place in acidic or basic solutions. I mean, there's always an element of acid or base, as you've seen from a Kw expression. And so in this case, we're going to balance the hydrogens by adding hydrogen ion. So we have 14 times H. So we're going to add 14 hydrogen ions. And there we go. So there's the balanced half reaction for converting chromium 3 plus to chromium 6. And so this happens in an acidic solution because there's hydrogen present, and it's in water because it's aqueous. So there's a nice little mnemonic for you to remember, or for you to help remembering what the order of things is for balancing a half reaction in these aqueous solutions. So first of all, that's where you balance the mass, and that's the mass of what's been oxidized or reduced. Second thing is you balance balance oxygens by adding water. Then you balance hydrogens by adding hydrogen ion. and then you balance electrons by adding electrons. Sorry, balance charge by adding electrons. So there we go. My Wallaby-Hurl's eggs, balance by mass, balance oxygen by adding water, balance hydrogens by adding hydrogen ion, balance charge by adding electrons. And so when you do all of that, you have a balanced half reaction. So this is in acidic or aqueous solutions. One more thing about aqueous solutions. So here, and we've already sort of looked at this, for the reaction shown here, what's the evidence there's reactions taking place in acidic conditions? Well, acidic conditions there's the evidence. Hydrogen ion, acidic. That means acidic. So if the question states balance the following half reaction in acidic solution or acidic conditions, you have to get two H plus being present, just H plus, amongst other things. So again, if we go through this my Wallaby-Hurl's eggs to balance this half reaction, so manganese plus 2, and in this case plus 7. So plus 7 to plus 2, that's a gain of electrons. That's actually reduction. Again, that gives you an idea where you're going to add electrons. So we balance by mass what's been oxidized or reduced. Well, it's manganese, it's already balanced. But now we have to balance oxygens by adding water. So if we add 4 H2O on the product side, we now have 4O and 4 times O, 4O. Hydrogen, 8 H plus. So 8 hydrogens, 4 times 2 is 8 hydrogens. Now we have an imbalance in charge, and we're going to balance by adding electrons. So 8 plus and 1 minus, that's 7 plus on the reactant side, and we have 2 plus on the product side. So how are we going to make 7 plus equal 2 plus? By adding negative charges. We're going to add 5 electrons to the reactant side. And it should make sense that the electrons are reactants because it's a reduction. Reduction, a gain of electron. There are the electrons that are going to be gained. And so it said acidic conditions, and it's acidic because of the presence of the H plus ion. So that's balancing a half reaction in acidic conditions. Well, what if it's basic? So here's another reaction. And what's the evidence that this is a basic solution? Well, it's right there, the 6 hydroxide ions. And so basic, presence of hydroxide. Now, how can you make an acidic solution basic? Well, here's what gives rise to acidity, the H plus. So if I want to make that a basic, I can add OH minus. Now, on the surface, this looks like a neutralization, and that's exactly what it is. It's a neutralization. But as you'll see, when we do this to a half reaction, we can't just add OH minus on one side of the reaction. We have to add it on both sides. So, here's another type of question you have to deal with. Balance the following half reaction in basic conditions. So the process is identical as for acidic. In fact, we get to acidic first, and then we make it basic. So, in terms of oxidation states, why don't we sign the oxidation states? So minus 2 for the oxygen. So that makes the carbon plus 3 for this ion. Minus 2 for the oxygens here, and that makes it plus 4 for a carbon in our carbonate ion. And so plus 4 to plus 3, plus 3 to plus 4, that's an oxidation. The oxidation state is increased, so that's a loss of electrons. So now we can go ahead and start balancing this equation. So again, remember, my Wallaby-Hurl's eggs. So mass, balance the carbons, and so now the carbons are balanced. Water, balance oxygen by adding water. Well, I have 4 oxygens here, I have 6 oxygens over here. So I'm going to add 2 waters to the reactant side. So 2 plus 4 equals 6. Hydrogens, I have 4 hydrogens. I'm going to add 4 hydrogen ions, plus 4H plus. There's my acidic solution. I still have to balance by charge. 2 minus, and this is 4 minus and 4 plus, 0. So overall, 2 minus on the left, 0 on the right. How do I make those equal? I add 2 electrons on the product side. And again, it's an oxidation. Oxidation products. One of the products of an oxidation are electrons, the loss of electrons. So now I don't have a basic solution, I have an acidic solution. I have 4H plus. But how do I make it basic? And so here's how we make it basic. So I want to get rid of that H plus, and I do so by adding 4 OH minus. So I've added 4 OH minus. Now here's the thing. 4 H plus and 4 H minus equals 4 waters. Okay, so I've got rid of that H plus as a reactant. But I can't, again, just decide I'm going to add something to one side. I'm basically pouring hydroxide into a beaker. So I have to add hydroxide to both sides of the equation. Okay, I don't want to change the reaction. I just want to add the same thing. So I add the same thing to both sides. And so now what you have is hydroxide left. So hydroxide remains. And if hydroxide remains, it's a basic solution. Now you may have noticed that we can simplify this, and I would never leave a balanced half reaction in a basic solution looking like that. So let's collect like terms and simplify everything. So we have 4 OH minus here. That's going to stay. We have water. We have 2 waters on this side, but we generated 4 waters on this side when we neutralized the acid. So in fact, we don't have any waters on this side, and we have 2 as products. We still have our C2O4 2-, and that's all we have on the reactant side. 2 carbon anion, no hydrogen anymore, it's water, so we have 2 H2O plus 2 electrons. And here's another word of advice. Whenever you rewrite an equation, be it a half reaction or a balanced chemical reaction, I would always check that it's still balanced when you finish writing it. So let's just check. We'll check by mass and charge. So in terms of mass, oxygen, 4 times oxygen plus 4 times oxygen. That's 8 oxygens. I have 6 plus 2, 8 oxygens. 4 hydrogen, 4 hydrogen. 2 carbons, 2 carbons. Charge, 4 minus and 2 minus. That's 6 minus charge. And the reactant side, I have 4 minus and 2 minus. That's 6 minus on the product side. So this is balanced. So that's a balanced half reaction, and it's in basic conditions. That means it's basic, just like the question asked. All right. So balancing half reactions, getting half reactions first of all from an equation, and then balancing them in aqueous solutions, or just as we did in the first instance with ions. It's pretty straightforward. You follow the process. My Wallaby hurls eggs. That's not a bad one to remember. That concludes this video.